All right, this is class 14, and I'm going to do the lecture part, and then I'm going to do examples as separate movies. So we're dealing with kinematics of rigid bodies, and this is the general plane motion, absolute and relative velocity. In class 13, we created the concept, or we introduced the concept that any kind of rigid body motion can be described using a combination of rotation and translation. So, and we made it clear that this fundamental equation right here for velocity represents translation, and this relative motion is the rotation right here. So we use that example, or we use that concept to try to break apart any kind of motion. So here is a couple of figures from the book, and to break this thing down, to break down motion. So we could think of this wheel that's moving from this position right here. It's moving over from A1 to A2, and B1 is moving from this position right here to a final position B2. We can make that a combination of that motion. So I will recreate these figures right here. And so this is us breaking the idea apart, that we moved from point A1 to point A2 right here. And so if that were to happen right here and there was only translation, then B would also move. So it would be B1 would move from right here to what we want to call B1 prime right there. And they both moved the same amount of distance that A2 did. Now, then so we want to address the rotational part of that. So we take that reference point and we put it onto a pivot right here. So now it's going to rotate about A2. And it will start off here at this B1 prime, and it'll rotate until it gets to this position right here, which we will call B2. And it moves a delta theta into that rotation. So you see that B2 ends up into the same location that we desired right here, but we've broken the thing down into these two parts, into the translation, where the whole thing moves together, and then when it gets to the destination in terms of its translation, then we pivot about the reference point and we rotate and get down to the final position. And one important note to make here is that we weren't tied to a particular point as being the reference. We could use any point on the body as the reference. Sometimes there's a good strategy in trying to break this down. So I'm going to show this same figure in two different ways, and we'll see how we could have gotten to the same final destination in two separate motions. So here in this first one, I will use A as the reference, okay? So this point A, moving from A1 to A2, it becomes the reference. So we're starting out right here is our initial position right here. So I'm going to draw that ghosted in our initial position, okay? And then we get to a final position right here. I guess I'll make it blue for translation, all right? So A moves over this amount from A1 to A2. It moves that distance. Well, B moves this same amount. So it moves from B1 to, let's call it B1 prime right there. And we could even say, okay, and then when we get into that position right up here, okay, here's the position here. Now this is we're going to pivot about A2. right here. So there's A2, and let's take out, oh, purple's a good color. We'll take out, and it rotates down this amount to get to B2, right? So this was B1 prime right here, and it made the journey over to there to get to B2. And that was through a delta theta right there. So it ends up in its final position based on this. And so we could have written this out right here. These are all positions, right? We're not dealing with velocities yet. We're just dealing with the motion of the thing. So we could say that the position vector that we had, this RB right there, it moved by way of taking RA as the reference, and then we added in RB with respect to A. That's what's happened in terms of like trying to locate a particular position right there. We could treat these as position vectors, and we're noticing that we had this relative motion right here, this RB with respect to A right there. Now let's try it the other way. All right, so we'll say, I don't know, I'll take red. So here's the initial position again, ghosted in. That's supposed to be this position right there. I guess it's kind of close. So that's B1, and this is A1. Now it's going to move down to its final B position right here. So let's make it this right here. So that means that B is going to move this amount. So we've, well, not ghosted. We'll make it full right there. Okay. So it has moved this amount. It has moved from here to down there. So that's going to be B2. And this is going to move here. Let's call this A1 prime. It's moved there. So from that new position right here, right, we're going to pivot from that reference point, right? So we took B and that as a reference in terms of its motion, so both of these move down the same amount that B would have moved down. And now we want to get to that other, the final position right here. We'll see that what we're doing is we're rotating right here a delta theta to get down there, and we moved from an A1 prime to the A2. So it's made this motion right there, and as a vector it would be straight right there. And so what we could say is that RA was equal to RB plus RA with respect to B, because B is the reference. B is the one that we used to move the thing to do the translation, and therefore we had to pivot about B in order to get, or well, let's say about B2, in order to get to the final destination. That's the concept. And you could see that we could use either one, A or B, to get to the final position. And there's a bunch of potato chips that are showing the same thing right there. So now if we do this instead with a delta time, well, okay, let me write this out. Okay, so buried inside here are triangles right here. So that same position vector. And notice there's little D's out in front of all of these, meaning that these are very small amounts of motion that were taking place. If we separate out that triangle right in there, we see that we have the DRB right there, and the DRA, and then we have a DRB with respect to A. If we take a small time increment, we could divide, well, we could write out this equation right here as DRB is equal to DRA plus D, that happens every now and then, I don't know why, DRB with respect to A. Here, we could divide all that by dt. Nothing's stopping us. And so we come up with the conclusion that VB is equal to VA plus VB with respect to A. And we'll find that we can find the magnitude of that with a angular velocity and a position vector. So we'll see that in the next slide, right? So using a 3-diagram method to break down velocity, we write down the velocity of B, okay, and we could have picked either one, but a lot of times perhaps we already know the translation of velocity, or we already know the velocity of A. So we'll use A as the reference in order to find B, and we add into that, and we say it's the velocity of B with respect to A right there, right? So what we've done is we say that we know A, so we apply the velocities in the second diagram of the one that we know, this guy right here, to both points, and then we pivot about that reference A, and we make a motion about that to be able to get that relative velocity. And note that that becomes a triangle right here. That same equation broken down as a vector triangle represented here. And something that we're going to find, we can always replace this with VBA is equal to the angular velocity of AB, right? And we can't call this a vector, by the way. That we can't give that a vector hat, with the cross product of RB with respect to A. One important aspect we can highlight here is that that right there is the same as this. We could also note that most of the time we're dealing in one plane, so that omega AB, as we've written it right there, is often going to be omega AB, the angular velocity, what happened there? The angular velocity magnitude times the unit vector K, right? So that's the unit vector that's coming out of the page. So if it's just plain, this is often the case right here. So we will often see that as we've written down below, VB with respect to A is equal to omega AB RB with respect to A. They end up being, we can know what those values are going to be. Oh, by the way, I should have put a K in there. So let me take that back. Sorry. If we want to get the magnitudes, VB with respect to A, we know it's just going to be omega AB RB with respect to A, all right? So we don't have to deal with the vectorness of this. If we only want the magnitudes of this, of the relative motion here, of this guy right here, we can always just take that angular velocity, omega AB, and multiply it by this distance right here, that B with respect to A. So, quite often with a link, right? Okay, so just a basic link. This is we were using potatoes up here to be potato chips to try to represent some generic piece. Quite often we're dealing with a link, and we might see two velocities onto this, and we will see the reference. So we want to use this 3-diagram technique primarily, and some of the other mathematical treatments of these, we could use them as alternate ways to solve this, but we keep going back to these 3 diagrams to try to reinforce the concept that we're dealing with translation in our second diagram and rotation in our third diagram. Right. So the way I've written this one down right here, we break this thing down, and as you've seen it drawn right here, you need to draw it yourself, but as it's drawn here, we can see that B must be the reference, because over here on the right hand side we've used that. So when we write an equation, it's actually for the point that we're not referencing, right? So we've drawn this thing out, but we're really writing an equation that's for this part of the link right here. So we're really writing out these three diagrams are represented by the velocity of A is equal to the velocity of B, right, because we're using that point at the top, plus the velocity of B with respect to A, right? And so that's the general equation here. We know that this is plane motion, so we could have alternatively just jumped to this equation right here, I guess I'll go AB, crossed with RB with respect to A. Pretty soon we will replace this with something we just recognize what direction things are going to go in. Okay, so anytime you see a velocity situation, we want to try to break it down into these three diagrams. And what's useful with this is if we have more than one link, which is might be possible in some type of mechanism, we can combine these together, and each one of these links has its own equation right there, right? So you could think of this first link right here. Whoops, let's go back to where we were. Where were we? There, boom. Let's say this guy right here is him, right? And so we're saying that this VO right here, here's the reference, and then maybe it has a motion of theta dot 1 right there. So its angle is changing. So based on this, and of course this is probably, it might be fixed, it could be, or could be rolling on the ground, so it only has an X component to it. So we will know this right here, and we'll be able to find out what the velocity of A is going to be. Now we want to find the velocity of B. We could then use A as the reference, because we just found it up above, and now we can find the velocity of B after, knowing what its angle is going to be. That should have been theta dot 1, and this is theta dot 2. Right here, and then similarly for C. And so that's like sort of a robotic arm kind of motion. We can create an equation that describes the motion of C. All right, so here's the big picture. There are several ways to approach rigid body motion kinematics. That could be confusing because we have more than one method, or we could think of it instead of being a negative, it could be a positive. We have multiple ways to find the velocity in something in rigid body motion. Therefore, we could use them as checks against each other. And so what I say, the way I'm breaking this down is I say I could use either vector components, which is like just going through the vector math, and you don't necessarily need to draw the three diagrams in that method, right? In many books, that's the way they'll approach. But Johnston decides to use these three diagrams, and I think it really does help to solidify what's taking place. So you're not just blindly following the sign conventions. But that's what you can do with vector components. You can just go through and use vector math. Another way is the diagram method. I like to say the three diagrams, right? The three diagrams, and that's really describing the relative motion between 2 points on the rigid body. And with that, you could actually use vector triangles. You could use the vectors and add them together as we've seen up here, right? We could use those three, the triangles. After we've made up these three diagrams, we can now focus in on the point in question right here, and that's going to be B, as we've drawn right here. Remember, that's the one that we're focusing on, that we're drawing the diagrams for. We can make the vector triangles for that. We can also use components, all right? And so that's actually the one that I prefer, and I think that we should treat as the main go-to application. There's nothing wrong with using vectors as cross products and kind of confusing. I call this vector components. But I would say, let me say this. This is vector math. Maybe that's what I mean by this first one. And the second one, I broke it down into two parts, vector triangles or vector components. And that's the one that I kind of think that we should go to. Alternatively, we will see in the next class, we have something called the instantaneous center of rotation. So that represents really a fourth way to calculate the velocities of a rigid body. I'm not going to go through this example, I don't think. It's in the book. They're describing the strategy to go over the sample problem. But here's the one that I will use. But I said that I will make separate videos for the examples. So I think I will stick by my word. So that's kind of the format here that I'm looking to create, is a lecture. This is a longer lecture video. And we will have smaller videos for the examples. So we'll pick it up here in a second. Sure, let's keep all of it. And close the video. And that was 20 minutes long.